Good day, students. On this clip, we're going to be going over part one of the two-part installment of finding equation of tangent planes and normal lines to a surface. So let's go ahead and take a look at the question that we're going to be doing today. The instructions are as follows. So in this problem, we are going to find. So this is example one. We're going to the find the equation of the tangent plane of the tangent plane and uh, a normal line of the surface um, f of xyz equals x squared plus y squared plus z minus 9 at the point p sub 0, the point 2, 1, and 4. Okay, so we have two things that we have to find. We have to find the equation of the tangent plane and then the equation of the normal line. Okay, and then yeah, normal line. I didn't write that completely. Also want to find the equation of tangent plane and normal line. Okay, let me write that again. All right, so now it's beneficial to be familiar with the concepts of gradient because this is the geometric significance of gradient that we're going to be using to create our normal vector here that's going to be used to write down the equation of the tangent plane and also the equation of the normal line. All right, so uh, just a side note, this equation right here, this is the equation of a circular paraboloid. This is a circular paraboloid. Okay, it's upside down and it's shifted 9 units up. So Uh, there you have it. Okay, so let's go ahead and try this problem. First thing we have to do is let's go over um, basically how to generate the equation of the tangent plane. All right. So in order to write an equation of any plane, you need the normal vector and basically use the components of I, J, and K to generate uh, the coefficients that you're going to multiply the coordinates by. So in this case, what on earth is going to be our normal vector here? Well, let's write this down. The tangent plane, the tangent plane to the surface, let's say an arbitrary surface f of xyz is perpendicular. It's perpendicular to the gradient. It's perpendicular to the gradient of f at p sub 0. So at whatever particular point you pick, the tangent plane to that surface at that point is always going to be perpendicular to the gradient. So in essence, the gradient is the normal vector that we're going to use to generate the equation of the tangent plane. All right. So let's write down the equation using this information that we have. So basically, the equation of the plane, the equation of the plane at p sub 0, let's say p sub 0 is x sub 0, y sub 0, and z sub 0, um, with a normal vector of the normal vector to the plane of, so this is the normal vector. The normal vector is basically going to be the gradient of f, okay? Because it turns out that the gradient is always normal to the tangent plane, all right? So with a normal vector to the plane of del f, which is equal to partial f, partial x in the I direction, plus partial f, partial y in the j direction, plus partial f, partial z in the k direction. Okay, this is a little bit long to write, especially when we're writing the formula. So we can just, this can also be written as f sub x, this is the partial respect to x in the I direction, plus f sub y, this is the partial respect to y in the j direction, plus um, f sub z, which is partial of z in the partial of f in the, with respect to z in the k direction. Okay, so if you have the equation of a plane at p sub 0 with a normal vector given by the gradient, can be written as, I'm going to use this notation for my formula because it's much more convenient. So the equation can be written as um, the partial in the x direction at the point p sub 0 times x minus x0 plus the partial with respect to y at the same point p sub 0 times y minus y sub 0 plus the partial with respect to z at point 0 times z minus z sub 0. All right, so this basically is the equation of the tangent plane. Okay, you see we got our normal vector from the gradient. Now this notation right here of writing down the, oh wait a minute, this is supposed to be equal to 0. Sorry about that. So this notation, so this whole thing equal to 0. This notation, this equation or this formulation of expressing the equation of the tangent plane, equation of a tangent plane is known as the component form. All right, this can be, this is known as the component form. This is the component form. All right. The much more concise form is also known as the vector form. That one kind of conceals a little part of the whole process. The vector form um, is written as, say, this whole equation is basically equivalent to the gradient of f um, at the point p sub 0. Um, p sub 0 is x sub 0, y sub 0, z sub 0. I could just write p sub 0 there, dotted with this vector, x minus x sub 0 in the I direction, plus y minus y sub 0 in the j direction, um, plus z minus z sub 0 in the k direction. Okay? So you can see that the equation of a plane is actually a dot product, right? We're dotting the unit vector with this vector, directional vector, from a point to any arbitrary x right there. All right? This is known as the vector form. This right here is the vector form. Okay? So if you work out the vector form, you're going to end up with a component form. But for today, we're going to be using the component form, which is a simplified, the worked out version of the vector form to do the problem. Okay, so that's the equation that we're going to be using for the whole process today. Okay, so it's equal to 0. And also we were asking the problem to find not just the equation of the tangent plane, but also the equation of the normal line. So let's also write down what the equation of the normal line is real quick, and then we're going to go ahead and do the computation. All right. So the equation, the equation of the normal line, of the normal line to the plane, tangent plane at p sub 0, which is x sub 0, y sub 0, z sub 0. Since we know that the Normal, the gradient is actually the vector that's contained within this line. So the gradient is basically what we're going to use to generate the equation of the normal line. So the equation of the normal line is simply going to be x equals x sub 0 plus a partial of x at t sub 0 times t. This is going to be a parametric equation. And then the y component is going to be y sub 0 plus the partial in the y direction at p sub 0 times t. And then z equals z sub 0 plus the partial in the z direction times, I mean, of p, partial in the z direction at p sub 0 times t. All right, so this is going to be the equation of the normal line, and that is the equation of the tangent plane. All right, so let's apply all this that we just derived to our problem. Okay, so first thing, obviously, we have to find is the gradient, right? Because the gradient is what we use to find the equation, and then also it's also what we put in here. This is the gradient right here, the partial with respect to x, y, z, and there goes the gradient here again showing up. So first step is to find the gradient. All right, so we could just write it down. Step one, find the gradient of f at p sub 0. All right. So remember what the gradient is. Del of f is a partial of the function in the x direction, that's I, uh, in the I direction plus the partial of the function in the with respect to y in the j direction plus the partial of the function with respect to z in the k direction. All right. So this is what we're going to be operating on the original function that we have. So it's basically going to the original function. Let me write it here again so I don't keep scrolling up and down. It's x squared plus y squared plus z minus 9. Okay? So the gradient at any point is going to be 2x. If we differentiate this function with respect to x, everything else is a constant. So we apply the power rule to x squared. So we get 2x partial x cancels out. So 2x in the I direction. I hat plus the same story with the y. We'll have 2y in the j direction. And if I apply the same process to z, z is just to the first power. I apply the power rule there, so we're just going to have 1 in the k direction. Derivative of, and then that's basically that, because this derivative of -9 is 0. All right, so this is a gradient at any point. Well, we want to fix it at p sub 0. P sub 0 in this problem was 2, 1, 4. So the gradient at this point will tell me the direction of the normal vector that will help me generate the equation of the normal line and the tangent plane, okay? So we need to um, complete step one. Step one was to find the gradient at this point. So the gradient of the function at 2, 1, 4 is what you get when you plug in these respective coordinates in this gradient vector that you generated here. So you're going to have 2 times 2 in the I direction plus 2 times 1 in the j direction plus k hat. K is independent of the point, okay? So if you simplify that, you're going to have 4i